In this video, we're going to derive the moment generating function for a Poisson random variable. So we're saying that x is a random variable, has a Poisson distribution with parameter lambda. Let's go straight in to getting the moment generating function. So the moment generating function, written as capital M sub x of t like this, is defined as the expected value of e to the power of t times x, as always. Now, because in this case, because x is Poisson, it is a discrete random variable. That means that the expected value is going to be in terms of a sum. And so also we need to work out what the sample space is for our Poisson distribution and what we're going to fill in here. So for a Poisson distribution, the sample space is when x is 0 all the way up to infinity, every natural number and 0 as well. So this is what we're summing over. And instead of x, when you do this, because normally if it's just the expected value of x, you just have an x here, it's just going to be e to the tx. And that's what's going to be timesing by our probability mass function. So the probability mass function for a Poisson random variable is e to the minus lambda times lambda to the x divided by x factorial. Okay, so this is what we need to actually try to compute. So hopefully we can rearrange this so we can get rid of the sum and make it a nice function in terms of just t. And of course, we can do that. So first of all, let's factor the e to the minus lambda to the outside of the sum because it is a constant, so we can certainly do that. And then I can rewrite my sum. So the sum from x equals 0 up to infinity. And what I'm going to do here is I'm going to notice that e to the tx and lambda to the x, they can be rewritten as two things times together to the power of x. So I can rewrite this as e to the t times lambda and then to the x. And that's still dividing by x factorial. Now, let's remind ourselves as another thing, which is that e to the power of, let's say, theta, I'll use theta here, can be rewritten in its Maclaurin series or Taylor series centered about 0 as the sum from, let's say, r equals 0 up to infinity of theta to the power of r over r factorial. Now, the reason I've mentioned this is because actually you can see that what we've got in our sum is basically the exact same, but we're not using theta, we're using e to the t times lambda. But other than that, it's the exact same. So I can rewrite this as e to the minus lambda, and this whole sum can just simply be rewritten as e to the power of e to the t lambda, okay? And then that can be rewritten as e to the power of e to the t lambda minus lambda. And this is e to the power of lambda times e to the t minus 1, like that. And because the Maclaurin series is valid for any value of theta in this case, that means it's also valid for any value of e to the t times lambda, which means it's valid for any value of t. So the domain of this function is that t can be any real number, and this function will still be convergent and it will still exist and be defined. So that means that the moment generating function, when x is a Poisson distributed random variable, it's e to the power of lambda times e to the t minus 1, like that. And t, again, can be any real number. Thank you so much for watching. I highly appreciate it, and I'll see you in the next one. Cheers.